Hey, how you doing? This is Tom. Welcome back. This is part 3 of building a neural network from scratch. In the last lesson, we talked about the data, we talked about how to create a training set and a test set. And in this lesson, what we're going to do is we're going to start building the neural network. Now, I assume that you have some knowledge of what a neural network is. If I say hidden layer or weights, you know what those are. Maybe you don't know all the details, but you kind of have a conceptual understanding of how things are put together. I'm also going to be using classes in this, so I'm going to make a class called neural network. If you don't understand what a class is, or you don't understand object-oriented programming, you'll probably be okay, but there might be some things like what I'm doing right now, this init, which is a constructor. You might not really understand what it's about. So if you'd like, go take a look really quick at a tutorial on classes, object-oriented programming, and Python, and then come back. All right, so what I'm going to do is I'm going to first send in my training data. So the training data, I'm going to save these as two variables, the input and the expected value. And then I'm going to go ahead and create the neural network down here. And I'm going to send those in, okay, like that. Okay, so all I've done is just send these values in, and I can print them out here if I'd like. So I'm going to go ahead and print out the input layer, and we're going to notice something here when I do this. You'll notice that this is not typically what you see when you print out a 2D list in Python, and that's because self.input, which is equal to input, which is equal to our training data here, that is not a regular 2D list in Python. It's actually a NumPy array. And that array, when you print things out, prints really nice and pretty. And it also gives us a few other things we can do, which are kind of interesting. So if I do self.input.shape, it'll tell me the dimensions of that matrix. So this matrix in this case is 1100 by 4, and in that case I have all of my input values there, and you notice that time it gave me a slightly different output, which is fine. You notice this is nicely formatted and everything like that. But the cool thing is you can still access everything just the same. If I want the very first row, I just use 0. I can still splice things like I would normally in Python lists. So everything works kind of the same, but the underlying features are expanded by NumPy. So there's more stuff that you can do with it. Okay, so that's kind of cool. Now, before I go on and actually build the rest of the feedforward process here, I want to talk about what this is going to look like. So we're going to build an input layer. And that input layer is going to have 4 possible inputs. So what I mean by that is every sample item, if we look at our network, there'll be 4 input nodes. So these 4 values will come in. And all of those input values are going to end up going to some set of weights. We're going to multiply all the input by some set of weights. And on the other side, we're going to get the hidden layer. So we have our hidden layer here, plus we have our activation function. Okay. And once again, on this side, we're going to get weights, and everything actually will go through the activation again, and that will give us our final output. Okay, so this is the whole process. We have a input layer, a hidden layer, and an output layer. And I've written this in the order that we're going to do things. So I can go ahead and put times here for the weights if we'd like. That might help us a little bit. So times the weights. But we don't really know, for example, what size we're going to use for the hidden layer. What size is the hidden layer going to be? You know that in neural networks we can pick the hidden layer size, however big we want. We do know that the output layer will be 1. Okay, so this hidden layer, you can put a different value in if you want, but just for the sake of clarity, I follow along for now, and we're going to put in a 4. So I'm going to have 4 hidden nodes in the layer. So this network is 4 inputs, 4 hidden, and 1 output. And we only have 1 output because the expected values can only be 0 or 1. All right, but this is a little bit misleading in the way that we're going to run things. Looking at this, you might think I'm going to take a single value, single input, simple data point, 4 features, whatever you want to think of it as, send it through the network, and then I'm going to do back propagation. I'm going to send it through the network and do back propagation. But we're actually going to do it a little bit different. What we're going to do is we're going to take all of our inputs as a matrix, which I just showed here. That's 1,100 by 4. And we're going to multiply that by our weights. So I'm going to take 1,104, so a matrix that big, and I'm going to multiply it by the weight set 1. So let's call this weights. And what that means is that this has to be 4 times something. Well, what I want it to be is actually 4 times the number of values in the hidden layer, how many number of nodes in the hidden layer. So this is going to be 4 times 4. And if I multiply this matrix times this matrix, if you remember anything about linear algebra, it's going to end up being these in the end. So the size of this hidden layer will actually be 1,100 times 4. Okay, so why am I doing it like this? Well, I could make a loop, and I could loop through all of my inputs and do it at one time. But that's actually really slow. And the truth is, there's not much of a benefit of doing all the feed forward step for one sample and then back propagation, then one and then back propagation. That's actually really slow, and there's no overall mathematical benefit for doing that. We can actually go ahead and do all of the inputs, and then we can do the back propagation all at one time. And by doing that, we can take advantage of NumPy and being able to very, very quickly multiply these really big matrices together. Okay, so if that's a little bit confusing, just kind of step back and think about how things are working. Really, all we're doing is multiplying and adding when we go through the feed forward process. If we do that all together at once and we get the output layer, which will have multiple zeros and ones at the end, then it's exact same. It's going to be exactly the same result. Okay. Now, the weights here, they have to be 4, and I'm actually going to make them 1 because this output layer is 1. And in the very end, our finished value will be 1,000 times 1. So we have 1,100 inputs, and with 4 features each, and we end up with 1,100 outputs at the end, which is exactly what we're looking for. All right, so let's go ahead and build the rest of this. And we've done the input layer, which is just this. We need to now build the weights. So we're gonna do self.weights1, and we're gonna use another NumPy function, and I'm gonna use this random here. So what I'm gonna do is I'm gonna show you these weights. Okay, so these weights, if I do this, you're gonna get values 0 to 1. We could have them -1 to +1, but we'll just stick with 0 to 1 for now. After we do the back propagation, all of these weights are going to change. It's possible that they end up becoming negative, or they go larger than 1 or anything like that. So right now, just random values are perfectly fine. Okay, and I also want to define these weights here. So I'm going to define those weights to random.rand 4 and 1. Now you're probably saying, well, why haven't you done the hidden layer? What about the hidden layer? What about the activation? What about the output layer? Well, we'll get to those in just a minute. For now, I just want to show you the input, expected, and the weight. So we've defined this, and this over here. Everything else is going to be defined in the feed forward process. So feed forward. And feed forward takes nothing but self. If you're kind of confused what this self is, it's just a way of referencing variables which are inside of a class. So if it says self, it's belonging to the neural network. Okay, All right, so feedforward really just takes 2 steps. The first step is getting our hidden layer. So this is going to be the hidden layer. And the hidden layer is multiplying the input layer by the weights. And to do that, we're going to use the dot product for with NumPy. And I do self.input. It's referencing this self.input up here. And self.weights 1. Okay, so I can go ahead and I can print that out, self.hidden. And I'm going to need to call it down here. So let me jump down here and we do feed forward. And I run this and I get this. So this is all of my input layer multiplied by the weights. And that means I'm going to get some pretty large values, some negative values here. I get some different stuff because this is just whatever the feature is. So if it's like this, it could be 0.52 multiplied by 3.62. Now, this is the hidden layer without the activation. And if you remember, an activation usually smashes the number between -1 and 1 or 0 and 1 or something like that. And the most common activation is the sigmoid. And we're going to use the sigmoid here. And unfortunately, NumPy doesn't have a built-in sigmoid. But we can go ahead and use our own, which will work just as well. And the nice thing about using NumPy is this will actually process this whole matrix, this entire 1100 by 4 matrix, and run every single individual number through this exponential here. So if I do this x is actually this whole matrix. And we're going to run it through this whole thing. And what it will do is it will take each of these individual values in this matrix. It will do the, the e to the power of negative 5.15. And it will add that to 1 and then 1 divided by all of that. And it will change all of these values to be between 0 and 1 for the sigma. And so what I have to do is this, sigmoid. And now if I run this again, you're going to see that these values, which are negative up to a positive, -5 to a +5 here, they are all going to get shrunk between 0 and 1, which is exactly what the sigmoid does. All right, so that's pretty cool. Now the hidden layer then gets multiplied by the second set of weights, and that will give us our output. So we're doing the same process, but this time it's going to be the hidden layer, and it's going to be multiplied by the second set of weights. And I'm going to change this to be output again. And you notice that this time we get a matrix that is going to be 1100 by 1. So it's just going to look like this. It's a single column of a whole bunch of values. And we still, let me run this a few times here. If I run this a few times, we're going to get some values that are larger than 1, some values that are close to 0, but we don't get any negative values like we did before. And that's because this has all been smashed through the activation, which puts it 0 to 1. And all of our weights are actually between 0 and 1 as well. So all the values are positive at this point. Okay, and as I said before, that might change. We still have to do the activation though before we get the output. So we do the same step we did there. And now all of these values, no matter how many times we run it, are going to be smashed between 0 and 1. All right, so that's not a lot of code, but it is a lot of stuff in there. A lot of stuff you may have never seen before, especially all these all the NumPy stuff, and just trying to figure out exactly the steps that I've taken here. So if you don't quite get it, walk back through, take a look at all these things. If you didn't understand some of the neural network terminology, go look at some of the links in the description and try to work those out before you go on to the next section, because backpropagation is more confusing than the feedforward part. All right, thanks for watching. If you got any questions, go ahead and ask them down below. Thanks.